So SENSE is by UKRI EPSRC for 3 years, £1 million, Network Plus, investigating the materials flows within the movable assets in the air, rail, road and marine sectors of transport systems. So we're not looking at the infrastructure, we're not looking at the rails or the buildings, but we are very keen to look at the materials flows, both vertically within sectors and also across sectors within these transport systems and between sectors. So today we have planned, we hope, what is an interesting day. You'll hear some of the initial reports from the feasibility studies that we funded. We funded 6 feasibility studies. I won't introduce them now, they're going to be introduced to you later. And essentially the Network Plus programme has a lot of money to give away. We have £1 million and about 3/4 of it, if not more, is going to be given away to people who want to do feasibility studies, small studies about £50,000 each, of areas that are of interest to the whole programme. We'll also cover some of the outputs from the road mapping sessions that were carried out at the later part of last year. We haven't got to the point where we've sort of consolidated the results, but we had some three very, very interesting and intense road mapping sessions, which Christine again facilitated with Richard, and we got some really fantastic sort of interactions. It's been a joy to work in a remote space, to be honest, to work in this way, because I think actually, although intense, and we've got some fantastic outputs and we've got good interactions, which is great. And I must say, I have to congratulate all the people that worked with us on those road mapping sessions, both the participants for being so interactive, but also the table facilitators, the postdocs who've been so fantastic at helping, supporting those discussions, and they will be helping, some of those will be helping today, and some new ones will be helping today in the interactive sessions today. And honestly, the job they do is really fantastic, and I really want to congratulate them and thank them very much for the time and the effort that they put in.
I would like to welcome everyone into our SENSE conference as well. Thank you for being here. I can see many people from the road mapping participants being present as well, which is great. My name is Petavratzi. I work for the British Geological Survey and I'm one of the co-investigators of the SENSE programme. My role in BGS is I work with mineral commodities, in particular a lot of the critical raw materials. And today I'm going to give you a very, very brief overview of what we've done with our road mapping just before Christmas. And the roadmap very much focused on material requirements for transport systems in 2050. The idea behind it is that, first of all, transport systems are very material intensive. They utilize a range of resources, a lot of them supplied from natural primary materials. We're also going through a transformation towards low carbon transport, and that introduced a lot of changes, the technology, but also the materials that we'll be using. And because of these two reasons, we know that material demand for transport systems is expected to increase quite substantially using different types of materials in the coming decades. Regarding material supply, well, there are a lot of different issues, and it's not physical availability. I can tell you that for sure, as someone that works with geologists. So combining all the different points together, there's a great opportunity for the circular economy to fill in some of the gaps regarding material supply. So part of this road mapping exercise, which by no means is complete or it's going to be the most detailed roadmap that's been produced, but we would like to create some sort of vision and some clear goals about what the role of the circular economy should be into to future material needs in transport systems to 2050. So what we did is that we said, right, that's it. We're going to develop, we're going to organize some sort of road mapping exercise. Initially, the plan was that this is going to be a natural series of events. Obviously, the whole timing fell during the pandemic, so we ended up having to do it virtually. That didn't put us off. We were very ambitious. So we set a series of steps, and we've started with a very brief online survey just to focus the topics of the roadmap exercise, because again, our time was limited to do that. And we had, as you can see on the right-hand side, the post-it notes photos. Obviously, you can't read any of this, but these are some of the responses we received from the survey. We had about, I think, 45 participants giving ideas during the survey period. And the 4 topics that have come up from this exercise were the ones I've listed in my screen. So material requirements for different transport systems in 2050. What the role requirements for transport in 2050 are, social trends and how these may influence materials in transport, and finally material supplies and how we can turn them, how can we incorporate circular economy principles in them. Following that online survey, we took the 4 topics and we organized a program of 3 virtual workshops. And these all took place in December, quite close one to each other. We had a series of participants. I'll talk a little bit about the participants later on, taking place with quite intense discussions. The workshops ran for 3 hours, and each workshop kind of followed from the previous one, actions from the previous one, so that we can move on with the exercise. We used the virtual whiteboard as we are going to do today, so the mural, and I've just put an example there, but you're going to look at them more closely when we go in later on into our discussions. And the road mapping process really during that sort of the different workshops was as follows. First of all, we looked at what our future vision of circular economy in transport is. Then we discussed what happens at the moment, so what's the present situation. We then tried to identify some enablers and challenges of our future vision. And then we took the top 3 of them, of 3 enablers and 3 challenges, and we went through some deep dive discussions, trying to analyze them in more detail, and later on try to find actions and priorities for addressing some of the challenges we identified into the short, medium, and long term. Overall, we've got ahead, as I said, 45 participants in our online survey, and we had more than 60 participants in total in the 3 virtual workshops. We're all working into different breakout groups. So the breakout groups were about 5 to 6 people, so that we can have a proper discussion onto the different issues we analyzed. We had participation from a range of different stakeholder groups, so a quite big group for research and academic institutes present with representation both from early career researchers but also from senior members. We had quite good government participation, so we had departments such as DEFRA, the Environment Agency, Innovate UK, Department of Transport, quite a few departments that took place during the road mapping exercise, and we had a quite substantial participation from industry, both SMEs but also large enterprises and industry associations. What we collected, as you can see also in the mural later on, is a quite substantial amount of information, and at the moment, consider that this has only taken place in December. We're in the process of actually analysing what has come back. What I've put on my screen is just some examples of the kind of things that we received back during this series of exercises for 2 different topics. So one was for the supply chain with C principles. You can see some of the actions and challenges that have been identified. So for instance, poor economics, and some actions that we've identified, such as, for instance, cost modeling of circular economy rates for materials, or finding ways to incentivize circular economy material procurement. On the circular economy material requirements, one of the big things that we discussed was producer responsibility for materials, and how important is that the UK develop their own rules or regulations around producer responsibility and for end-of-life vehicles. So these are some of the examples, and they may be useful for the next round of feasibility studies, but I'll go back to that later on in our conference today, because we will be introducing the next call of feasibility studies. And I'm sure as time passes by, so we'll be able to share some more of these findings with you too. So where are we at the moment? Well, at the moment, as I said, we're in the process of actually analyzing all the information that we've collected. We are following that initial analysis. We're going to try to synthesize the key findings into a draft roadmap, which we would like to disseminate with participants in our conference, but also the people that took part in our road mapping exercise, and key stakeholder groups from government, industry and funding bodies as well. And we're also planning a series of follow-on events. It's very likely we'll have to have some additional discussions with some stakeholder groups, but also we are planning to have another 3 road mapping exercises coming up. And I suspect that some of the findings from that first road mapping exercise will inform the forthcoming exercises too. So that's all I wanted to say today. As I said, there was quite good big group of people that participated in this roadmap. A lot of early career researchers, that they helped us and they took notes and they helped with the process, of many thanks to them, but also to our participants. And Christine and her team, that they worked and helped us develop the road mapping exercise virtually. Thank you very much.
Plus, there are 5 areas of activity planned for SENSE, and we've heard about the road mapping from Evie. This one is about our sort of small project activity, and that was launched with the feasibility studies. This is the things we're going to hear about are the first 6 that were funded in round 1, and there will be 3 rounds of feasibility studies, so there will be ongoing opportunities for members of SENSE and participants to apply for their own feasibility studies. Just to give you a brief overview of it, we received about 25 applications. They were reviewed by the management team of SENSE, and as I said, 6 were funded. The basis for them is it's an open call. There was up to £50,000 available for the feasibility studies, and they're intended to run over 6 months. As you can imagine, COVID has managed to intrude on our magnificent plans for feasibility studies, and so they started in late July, August last year, and we've allowed a little bit of extension for pretty much all of them, and they'll be reporting fully likely by the end of February, I view. They're all in progress at the moment. The teams have been working very hard on them, and we're very fortunate to be able to hear from them all here. They've been given a strict brief to present their feasibility study at this stage, so something between 5 and 7 minutes, 3 PowerPoint slides, and there's a graphical abstract on the mural as well. So there's good material there for the breakout discussions that
looking at wastewater derived ammonia, so from contaminant to a carbon-free transportation fuel. And so ammonia has long been considered as an alternative transport fuel. It's got a volumetric energy density almost twice that of hydrogen. And due to its widespread use in agriculture, there's already a quite well-developed supply chain and infrastructure for its distribution. So it can either be applied within an internal combustion engine, such as during World War II in Belgium, where due to fuel shortages, they converted the internal combustion engine of buses to utilize ammonia, or can be used within a fuel cell for direct electrical generation. So, such as Toyota have produced an ammonia fuel cell electric vehicle, which utilizes ammonia to store energy as a fuel, converts it to hydrogen in situ. And the other option is to use the ammonia directly in a
Hi everybody, my name is Pierre Josso, and today I'll be presenting our feasibility study, which was done at BGS with other members of my team here. And the objective was to look at the past and the impact of extreme shocks on raw material supply chain for the transport manufacturing sector. So in terms of context, the global aim to decarbonize the UK economy, really to tackle climate change, will require fundamental changes to our transport infrastructures and energy production, which will require vast quantities of raw material, really. The current sanitary crisis that we are all experiencing at the moment is unprecedented by its scale, and it has put the world to a halt, shutting down international transport, disrupting trade with Far East countries, entering lockdown cycles at different rates all over the world. So this situation has really highlighted the complexity of our supply routes, I would say, and questioned the security of our supply in critical raw material, which are essential to meet our decarbonizing objectives. So for this feasibility study, we were trying to look back at recent history and analyze how the past major pandemic and economic crises have affected the supply of raw material. So to do this, we've used BGS mineral intelligence and historic records of mineral production per countries since 1913 and done some statistical analysis and compiled that in different proxies, etc., which I'll show you briefly. Right, so we focused our study on aluminium, cobalt, and nickel, which are three metals which are essential for transport in the aeronautic, automotive sectors, and all the others. And we considered the following shocks that you can see here on this graph, and they include world wars, major epidemic, and economic events. There's quite an increase of event in frequency over the last few years, as you can see. But it has this quite a large range of events, and the drivers for mineral commodity markets are quite diverse, complex, and my time is quite limited. I will briefly highlight some of the major findings. Right, so on this graph, if everybody's on this graph at the moment, so you can see, for instance, aluminium global production over time, which is the black curve, which is growing exponentially, which is following nicely the global world demographic. In blue, you have the percentage change in production relative to the year before, so it's kind of an update on what the production is doing. And in green, we have the oil prices. So one of the major findings, and also the horizontal bars correspond to the different events that we've considered in the timeline. So the major finding is that actually none of the major past pandemic, such as the influenza outbreak of 1957 or 1968, the SRAS in 2003, and Ebola in 2014 had any measurable impact on supply. Whether we consider just the global volume that has been produced, or also the concentration or diversification of the market, because we also looked at the number of producing countries and their relative shares. So there has been no real measurable impact of major past pandemic. So one of the noticeable exception to that, however, is the Spanish flu of 1918-1920, which made millions of dead throughout the world, which is quite sad, but its economic impact is unfortunately quite difficult to deconvolute from that of the end of World War I and the transition between war and peacetime economies and the associated recession. Alternatively, as we can see from the blue line, the year-on-year change, and when we look at all the vertical gray bar, is that most economic shocks have had a major impact. Notably, it's interesting to highlight the two energy crises of 1974 and 1979, which deeply transformed the aluminium sector, for instance, and had a similar impact on cobalt and nickel. We see a consecutive rise in oil prices by a factor 4 in over a decade, which had an impact obviously on global production and initiated a major diversification of the market. We see a lot more new countries entering the production and a geographic shift in the production center towards countries with access to cheap energy. And this is just a highlight of the latest energy crisis of 1979, where you can see on this graph production normalized to the year before, the event, and you see a massive drop of 15 to 35% production in activity and a 2 to 3 year recovery depending on the type of commodity considered. And such response is common to all markets and economic crises that we have considered in this feasibility study, and we will be using this data to tailor different scenarios for our COVID recovery. So overall, most shocks have followed kind of a similar pattern from a global economic point of view, which can be summarized by this diagram. In the first phase, we see the crisis unfolds, which is leading to major drop in values of commodities, devaluation of mining-related currencies, and oil prices. We actually saw all these happen from January through April last year. And this is followed by a demand shock as a result of depressed economic demand and growth. And in phase 3, we usually see the alignment of industries to the new demand levels, which is favoring the most profitable project and causing the others. And this has knock-on effects on trade routes, whilst most governments are trying to stimulate the economy to try to minimize damages. And phase 4 is the one towards if everybody is thriving at the moment and correspond to demand rebound, leading to minor shortages of the commodity, rising prices, and new investments. So back to kind of the new normal, I would say. At the moment, we are experiencing, well, we are in the middle of phase 2, and a bit of phase 3 has, the lockdown measures have drastically impacted demand, and industry and governments have started to react to it. The big question for our scenarios really is not if the market will recover, but when, as time is the big unknown in this equation. On one hand, there is hope for kind of a quick recovery as vaccines are starting to roll out. And China as well, the big player in the mineral commodity markets, has been relatively untouched since spring last year. Notably, as well, it's important to point out that most commodities have already recovered to pre-pandemic prices at the moment. So the problem is that the ongoing, still going restrictive measures in Europe are actually leading to a major economic recession, which may last for years.
Yeah, your time is up.
All right, just briefly concluding now, at the moment we're compiling all our results into manuscript for potential publication and developing our different scenarios, including consumer behavior and change on the circular economy, how it's going to impact recovery, and we will try to map out the detailed network of nickel supply routes to identify potential bottlenecks and help diversification. Right, thanks.
Good morning. My name is Jean Marshall. I'm going to talk about our project in smart and sustainable coatings. As part of this project, we have researched the current state of the art in this field along with future developments, and we have also looked at business engagement with this topic as well. So just to give you an idea of the experience in our team, between our team and WMG and also our colleagues at the University of Exeter, we have a breadth of understanding and knowledge in both polymer science and material science, but also in innovation and business engagement as well. So as most of this audience will be aware, in transport applications, quite a lot of components are made from composite materials. And these often undergo finishing processes for either aesthetic or protective reasons. However, when a component comes to the end of its useful life and needs to be recycled, we need to take the whole material system into account, not just what the main body of the component is made of. Coatings can actually limit the recyclability of components by creating mixed waste streams. One particularly important example of that is if the component itself is thermoplastic, then it can be reshaped, remolded, recycled when it's heated up. But if the coating is thermoset, in other words, it doesn't change its shape when heated, then that creates a mixed waste stream and can limit the recyclability of even a thermoplastic recyclable component. So a lot of large suppliers of raw materials for coatings have realised that sustainability is an issue, and various developments have been made over the last sort of few years, couple of decades, in terms of trying to make coatings more sustainable. For example, things like UV curable coatings that don't require volatile solvents in there, replacing volatile solvents with water-based formulations, trying to replace traditional synthetic resins with biological derived resins for binders, this kind of thing. In the future, sort of slightly more futuristic ideas may include things like trying to make your components so that it doesn't need a coating, trying to change the material formulations even more, or possibly even manipulating the surface so that, for example, surface roughness gives you an aesthetic effect rather than having to use a coating. Alternatively, coatings could become stick-on so that there's no energy-intensive process involved with recycling them. Now, as I mentioned, currently the trend in components is away from thermosets and towards thermoplastics. Thermosets do have advantages, however. They can be more robust, more scratch resistant. And so over the last few years, a lot of people have become interested in this technology called vitrimers, which can combine virtues of both. And I will discuss that a little bit more in a moment. But this isn't just an academic interest, and it is becoming commercialized, increasingly commercialized in the last couple of years. So what's a vitrimer? I think it can be thought of as a cross-linked polymer network, which has bonds that can exchange, can break and reform when the temperature becomes high enough. So at the working temperature of the component, the material behaves like a thermoset and is robust and strong. But when it's heated above a certain temperature, then it gains some thermoplasticity. It can be remolded and recycled. So just to give you an idea of the interest in these materials, this graph shows the results of a SciFinder search on the keyword vitrimer. And you can see that, and the results are grouped by date. You can see that in the last 3 or 4 years, then the number of academic articles and patents on vitrimers has actually increased quite a bit. The arrows on the diagram give an indication of when certain sectors started to show an interest in commercializing this technology. I want to watch maybe the US startup company Melinda, which just secured a large investment from SABIC recently to develop vitrimers with a particular focus on the automotive industry. However, once you've invented a sustainable or recyclable component, it's not enough to invent such a material and then assume that it will automatically be recycled. You need the infrastructure in place to ensure that it is recycled. And in order to efficiently use raw materials, there needs to be processes in place to look at extending component life where possible, reusing components when possible, but then actually recycling the materials afterwards, which even in the case of a vitrimer material may mean separating the coating from the component, or if the vitrimer is sufficiently well thermoplastic, it may be possible to recycle them together, but then you end up with a mixed waste stream. And there has to be a sort of some focus on second life for those materials. So as part of this work, we've also spoken to various business partners across transport sectors and identified some common challenges in using sustainable coatings, such as finding good second uses for these kind of materials, low value material, because obviously if you try and reclaim a material from a coating, you only get a small amount, so it can become economic to do the recycling. But there are also further specific challenges identified by some industries, such as whether or not customers themselves are actually interested in the sustainability of their coatings. So that's been interesting to find out the specific challenges there. And just to quickly finish, just to summarize some of the outputs that we've created across this project, we have a couple of papers that are currently in preparation and will be submitted soon. We've submitted a few bids for further funding to develop this work, participated in some research development programs. We would like to acknowledge UKRI, EPSRC and the Circular Economy Network in Transport for funding this work, and also to thank industrial partners who've given their time to speak with us. And thank you for your attention.
University of Strathclyde, and we're focusing on, as a team, we're focusing on the potential for zero waste decommissioning of commercial aircraft, which is quite a challenge, and it's an ambition to achieve. On this call, we also have Paul and Lee, who are both attending today's session as well. Fiona is not. So it's very topical. I mean, it's almost every week in the newspapers or on BBC, you see all these planes lined up at airfields, and in typical in a normal year, between 800 and 1,000 aircraft, commercial aircraft, are retired, which means reach the end of their useful life and then go into the next stage, which, as you can see at the bottom of the graphics, is in parked for 1 to 2, 3 years, either go back into operation, but most of those have been retired and broken down and parted out. So the good parts are taken and reused, and then that's where the challenge becomes what's left. There's claims that as an industry, between 70 and 85% of the aircraft is recycled. I put it in quotes because I don't know what recycled means. It could mean burning it. It could be landfilling it. It's not clear what is meant. So there's a lot of bad practices in the industry and a lot of potential where recovery could be carried out, which is not being carried out. Now, of course, last year we had the big impact of COVID, which has meant more than the typical 800 to 1,000 aircraft, we may be seeing between 5,000 and 7,000 additional aircraft being retired. And that's going to cause a big problem. Graveyards or aircraft graveyards are filling up, but really that's only a short-term solution. Most aircraft are owned by leasing companies, or the airlines own less than most people realize. For example, Thomas Cook only owned 3 aircraft, which we've been decommissioning, which I'll show you shortly. These companies are keen to get more value out of their assets. So if they could recover more of the material, then it's obviously a business case for them. Plus, it ticks the box with sustainability. Now, you may be surprised, but the UK is number 3 in the world in aircraft decommissioning. We decommission about 120 a year at 2 or 3 locations in Wales and in Gloucestershire. And these really 2 main operators dominate the field. The best in class for reuse is something called Tarmac Aerosave, which is a spin out from Airbus, came up through an EU project called Pamela, where they claim they can get up to about 85% recycling. The UK companies are still reluctant to tell you that share, but we know a lot of things do end up in landfill. The graphics on the right-hand side is just some of the latest data showing you that most of the aircraft being retired, no surprise, are the older, less efficient aircraft. But we will see a trend, of course, towards more advanced aircraft with more composites involved coming into the retirement in the next 5 to 10 years. How you decommission? There's a few strategies. If we look at the impact, the easiest way is just to shred it, which is the most energy inefficient, the most environmentally inefficient, because what you're doing, you mix all your materials up and you then have to somehow separate them and reuse them. The best is systematic disassembly. Where you break it down in terms of materials and use that as a basis. But of course, the economic cost goes up. And during the breakout sessions, I was discussing with one of the colleagues about that trade-off between what is the most efficient way of doing it in terms of environmental recycling and what is the most economic. And in between, we have different strategies such as smart shredding, where you choose different areas to remove, gross cutting, detailed cutting, which is self-explanatory, and smart disassembly. So a lot of these practices are not widely used in industry, and part of this is productivity gains and also demand for the materials, but this is changing. Typically, decommissioning takes around 30 to 40 days to decommission an aircraft. The pictures on the right-hand side are where the team went down to Manchester Airport. This would never ever happen in Manchester Airport under normal circumstances. No passengers want to see aircraft being cut up next to the planes they're sitting on. So only because the airport has shut down, practically because of COVID, are we allowed to decommission aircraft there. And 1,000 parts are taken straight away. The remaining, the fuselage, the seats, the wings, the interior panels, which are composite, and floorboards, that's the challenge. How do you get that back into the supply chain? Even the computer screens, the TV screens on the back of the chairs, all that is wasted. There are some creative usages which are coming out, but the challenge is it's always low volume. I mean, you can make fancy desks if you want to with a part of an aircraft fuselage in front of you. I'm sure the demand for those is not going to be the equivalent to going to IKEA and buying one of these in kit form. So there is that challenge about how much material, how many can be reused in these purposes. So we've been talking to organizations which are looking at concepts such as putting offices into shopping malls as a way to deal with you know, the fact that people are probably getting sick and tired of sitting at kitchen tables doing their work. Can we repurpose some of this material to create those very easy to clean and sanitize office furniture? I'm finishing ahead of time, looks of it. We started the project relatively late compared to the rest, and we'll be finishing in March. We are now looking into more detail at some of the waste streams. So we have a team looking at analysis of that. And also the supply chain. Where are the gaps which exist to take some of these material and these parts which could be reused, repurposed, but where are those gaps in particular? And that's us going out, reaching to lots of companies. We're also looking at the trends in material usage. We know that 777, which came out in 1997, has around 12% composites, but the newer generation have around 45% composites. And also looking at the current inefficiencies in the assembly process. The picture on the right-hand side is not just for the sake of it. I'm buying an Airbus A320 to decommission. So it's a real example, and we're just going for the motion. This project does not give enough money to do that, but I found additional funds to help us do that. So we're actually going through the whole process of decommissioning the aircraft over the next 2 to 3 months, understanding firsthand what's going on and bringing supply chain companies into it to say, look, this is the potential. And I'm finishing with 8 seconds left. Thank you.
Hello, everyone, and thank you for the opportunity of developing this research. I'm Artem Alsbach from the Royal College of Art, and I will present in the name of my team, Eco-fitting Whole Life Design, Upgrading Cars to Zero Emission. So the UK requirements for ultra-low emissions will create a fleet of 15 million compliant ICE cars in the UK. Eco-fitting proposes a new circular economy strategy to contribute towards zero emission in a sustainable manner by retrofitting the existing fleet of ICE cars. This involves not just electrification, but importantly, customization and personalization of these vehicles to create desirability, promote behavior change, and long-term ownership. As such, design is at the heart of eco-fitting. Converting cars to electric is a growing trend in small business and OEM, and this project aims to expand this trend beyond classic cars. To investigate the feasibility of eco-fitting, the research explored possible design directions to demonstrate this potential. We identify that the cars from '98, which don't fall into the classic cars exemption, are worth candidates for eco-fitting. And to visualize what can be done with this fleet is how design research can investigate the feasibility of eco-fitting. We started our design research process comparing eco-fitting to ICE and EV strategies. To look at all aspects of sustainable design, we expanded the toolkit developed by Carlo Vezzoli to a quadruple bottom line of sustainability, as suggested by Stuart Walker, then including also subjective sustainability. The highlight of the study shows that on environmental sustainability, the best of eco-fitting comes from the benefits of long-term ownership and waste and resource reduction. And for economic sustainability, the benefits are local production and the wider distribution of opportunities. So in socio-ethical sustainability, the promotion of local culture, communities, and responsible consumption. And finally, from subjective sustainability, the promotion of an aesthetic of sustainability and valorization of identity and deeper values. And then the following state-of-the-art research look at trends supporting eco-fitting. We classify the current retrofitting trends, which you see on the screen, and identify the opportunity to expand, which you see in blue on the screen, which are with different costs and probably more interesting. We then set 4 design briefs inspired by the material culture and behavior trends observed in the research. Those are very different from the industry offer that in fact is not aligned to the aspiration of young consumers or the dream of car enthusiasts. Those are the briefs. Metamorphosis is an intense transformation of a vehicle focused on performance and high technology. Symbiosis is about harmony between new and old, where donor cars get additions of sustainable material, but keeping most of the original car. Upcycling, it's about reclaimed vehicles, reclaimed parts, and celebrating agingless cars. And finally, art cards is about personal expression, and is a statement at the same time the highest added value. I think you want to see the design, so we're going to quickly show that. So this is our upcycled Golf, a reclaim and finish restoration project turning into a SUV substitute, incorporating a sub-chassis to battery and reclaim parts and wood. This is a DIY project which will benefit from an eco-fitting network of suppliers and garages. This is our art car, most fun inspired by one of our interviews, and the biophotovoltaics most stable, mixing art, technology and nature, displaying the dream of clean energy. This is the Symbiosis 500. It could be developed through a dealership service, offering options of customization from a wider network of suppliers and powertrains from OEMs. And finally, this is the Metamorphosis MG. It would have a design and modified body to improve aerodynamics and sustainable materials in the interior and updated interfaces. These are the few of the possibilities that we saw from the eco-fitting landscape, which I want to activate in the next steps of the project. So the planning research activities are developing an eco-fitting demonstrator to promote the concept, develop an eco-fitting circular economy strategies engagement to promote circularity, and a quadruple bottom line of sustainability. The design toolkit will be developed to promote the knowledge that we're looking at. The opportunities are around non-compliant vehicles can be redefined, promoting zero-emission mobilities, develop social responsible material culture, promote long-term ownership, changing the way cars are designed in the future. And the circularity in the product level needs a support platform and evolve culture. Our beneficiaries, which you can see on the landscape on the side, are OEMs, extended supply chain, garages, dealerships, customizers, restorers, retrofitters, and design studios. The pathways that we envisage to impact this is the feasibility study, following physical demonstrator and stakeholders engagement, then industry partners project, and a design of an eco-fitting platform, and then working on policy making and developing of incentives. Well, this is pretty much the summary of what we have developed so far. Look forward to publish the report. Thank you very much.
Thank you, everybody. So our presentation or our feasibility study is looking at circular materials across transportation machines. I'm just going to go through the presentation in 7 minutes, hopefully. So the project team draws together an interdisciplinary research colleagues from 3 different schools at Loughborough University, and led by my colleague Catherine as the research associate. So the aim of the project is to develop a methodological approach to advance the circularity of materials used in transportation machines. We're talking about transportation machines, automotive, trains, aircraft, and ships across the 4 transportation modes. So there are 3 key objectives which are in line with the work packages to address the aim. And these are, first of all, looking at cross-transportation machine and material circularity identification, then prioritization. Then this is the whole feasibility studies is underpinned by a novel concept. We're calling it ROSE: re-engineer, optimize, and share and exchange. and then we'll be using a case study of materials, and then the feasibility study will culminate into the development of a scenario-based roadmap for the prioritized materials. The project is supported by 7 industrial partners who have been involved for the moment in 3 project meetings since we started. And then this is the approach, what we are calling it, the hierarchy of our feasibility studies, threefold. The first aspect, part of WP1, is looking at identification of
1656
cross transportation machines in terms of communalities. Then we looked at widely used materials across the 4 sectors, or the 4 transportation machine. And then we prioritize some of these materials that we're going to look at. So we've already, WP1 has culminated in a milestone 1 report, and then we are now looking at implementing the ROSE framework, which are going to be followed up by the roadmap. So just a summary of the assessment criteria in terms of potential circularity of these materials. So we looked at 5 criteria: material circularity, material demand, material use, current waste recovery, and the environmental impact. We looked at 5 different materials used: steel, aluminum, composite, plastics, and glass. But here is the 4 key materials that we looked at in more details. And then the prioritization based on the selection criteria has selected 2, culminated in 2 materials, steel and plastics, across the life cycle stages of the materials. So design, manufacturing, and end of life. So we looked at opportunities across all the life cycle stages of the 4 materials. During the design, we looked mainly about material efficiency and the optimization. And then during the manufacturing, we looked at the recycled content mainly, and end of life, reuse, remanufacturing, and the recycling. And based on the prioritization criteria that we allocated for all this, we identified steel and plastic as being high in terms of economic potential. So from that, we focus on these 2 materials, steel and plastics. So you can see the focus for steel will be on design and of life, and it's related to automotive, rail, and maritime sector to some extent. And plastic will be mainly used in automotive and aerospace. And from that, like I said, the whole case study will be focused on the key framework of this feasibility study, which is the ROSE. So steel, plastics. So we start by doing the design. It's the first stage of the ROSE framework, is the re-engineering processes through eco-design, which is very common denominator to a lot of case feasibility studies that we discussed this morning, looking at design for disassembly, designing out waste. Then we're looking at manufacturing with use as well, is the optimization components of the ROSE, and looking at how to make resource efficient production, durability of these materials, 3D printing mainly for plastics, and manufacturing out waste, and so forth. And then finally, at the end of life, so how can we share materials between different transportation machine, and how can we exchange the raw materials, secondary raw materials between this in a closed loop between the different transportation machine, and maybe in the longer run in the open loop between different other sectors. And then now I'm going to pass you through my colleague, Andrew, who will talk about scenario-based roadmap. Andrew.
Thank you very much, Mo. So essentially what we've been talking about, I suppose, in all of these presentations this morning is this idea of the circular economy. And I suppose we've been using it as this singular vision, But actually, what does the circular economy mean in practice? Well, there are multiple different pathways that we could take to get there. So this is some ongoing work at the moment. So we've been developing these scenarios of what the circular economy could look like in practice in transport, machine manufacturing. So we've got these two critical factors which have been identified throughout the work from earlier work packages. One is around supply chain integration. So how well are OEMs integrated within the design process with tier 1, tier 2, tier 3 suppliers, and originally kind of raw material suppliers. So this idea of how do we embed the ROSE framework across the supply chain. So that could go from low to high. And likewise, our supply chain integration globally. Do we have a globalized supply chain or a local one? So we already see some issues, kind of resource nationalism. So we've developed these 4 scenarios, and we're focused on scenario 1 at the moment to utilize that to develop our roadmap of this is our vision for the future. How do we get there? So on the right hand side, you'll see at the moment kind of our draft framework of our roadmap. We've got our vision statement about integrating life cycle design to optimize material usage for circularity. So we've been identifying with our questionnaire and consultation with our research partners kind of our cross-cutting actions, and then underpinning is our kind of mode-specific ROSE framework as well. So these are kind of the key outputs which will be coming out of.
That's great.
Thank you very much indeed.
I've got a statement which is about what the rationale for the network is, and it comes out like this. I'm going to read it verbatim because I think it's a good statement. Whilst easy mobility has become a way of life for many, the machines that enable this are both highly resource consuming and environmentally damaging in production, use, and at the end of their working lives. Attention has been paid to increasing the energy efficiencies of these systems, and we all know about the legislation for tailpipe emissions and things, but the same effort has not been put into optimizing the resources and the resource efficiency. Numerous potential benefits could be realized if the circular economy principles were integrated, and the sense will be forward-looking in terms of developing future designs, future business models, and future manufacturing and process approaches, so that emergent transport systems are inherently circular. So this innovation cafe session is all about how we might stimulate the ideas. I mean, some of the conversations I've just been in, just in the last session, were actually getting to that point about looking at things like a circularity index. How do we create a circularity index that people can use at the before we have a design? You know, what do we use to have a circularity index that takes into consideration maybe the 3 pillars of sustainability, or even the 4 that Artur was talking about in his project? So what interesting areas do we think could be useful and valuable for the next round of feasibility studies to support the design and business models and the manufacturing, so that in the end we actually end up with a circular transportation systems?
We're having 3 altogether in this project, so that's going to be the second one, and we're hoping to open it on the 15th of February. And there will be information on our website. As with this round of feasibility studies, and you've seen the results for the ones who found it already, they have a duration of about 6 months. The projects are around the 50K that we're funding, and that's at full economic cost. And we're hoping to fund another 4 to 6 projects in that round. And we really want to see early career researchers having either leading or having a very strong involvement in the development of the projects. The research strands that we've introduced in SENSE are as follows. So we've got a research on material flows and stocks in transportation, whole life design, circular economy decisions, circular economy transitions, and digital circularity. So projects around these themes are very welcome. Please be aware that things such as fuels and infrastructure, transport infrastructure are out of scope. And I'm highlighting this because last time we had some interesting proposals, but unfortunately they were either related to infrastructure or transport fuel, so therefore we couldn't fund them. The other thing I would like to say is that we are also interested to see whether any feasibility studies will initiate from the findings of our roadmap. As I said in my presentation earlier this morning, the topics that we've identified throughout the survey and the workshops are material requirements for transport, the role of circular economy to satisfy material needs, supply chains with circular economy principles and social trends and how they influence material choices. And I've picked up some of the challenges or enablers that have come up through our discussion. By no means this is the complete list, but I thought that some of them make interesting projects. So things such as LCA studies, there was a lot of discussion even today about that, material passports and standardization, the role of ownership to the future of transport, foresight studies, economic modeling, design, so the role of modular design, etc. All these can be topics that may be relevant for the new round of feasibility studies. So looking forward to your proposals. I think once the call is open, we'll be giving you about a month, Rika, is that okay? Is that right? For people to develop their ideas and submit them, and then we'll fab them after that. So that's all I wanted to say.
Okay, so thanks very much. I mean, basically, I want to thank all the participants first. We hope that you've enjoyed the sessions and the discussions. We'd urge you to watch out for the announcement of the next round of the feasibility studies, which Yves just said will be around about the 15th of February. Do make sure that the projects that you put together are truly about circular economy and not just about one mono aspect of lightweighting to improve fuel efficiency or something like that. Please make sure they really do follow the principles of the circular economy and read through the stuff about circular economy on the website, and also have a look on the mural to see what the ideas are that come out of the mural, as Evie has said. They're really useful. We urge you to join the Sense network if you haven't already joined. Make sure that you get onto the network, make sure you get all the messages from Rika. Follow the Sense Twitter handle. We've got a Twitter handle, C for Transport, I think it's called. Is it C for Circuit? I can't remember what it is now.
C for Transport.
C for Transport. So C and then
C,
a 4.
Number 4.
Number 4 and then Transport. And follow the Twitter handle. Follow any of the co-Is who have Twitter handles as well. So I tweet, and so does, and also Christine tweets about this, and Rika tweets. So and Steve Evans occasionally tweets. Richard tweets. So do follow us. I think Evie tweets, but I'm not sure. Kerry doesn't tweet so much. He's a quiet bird. Anyway, so do follow us. I'd like to thank all the table hosts as well. I think you've been fantastic. Thank you very much for your sort of sterling work in keeping the discussions going and making sure that the mural has been populated. So perhaps we can give everybody a round of, all the table hosts a round of applause. Thank you very much. I'd also like to thank my co-conspirators, Richard and Evie, for their work in introducing the different sessions. And of course, thanks must go to Christine, Kermit, Bell, and Richard for facilitating or coping with the technical challenges that today really presented. And goodbye, stay safe, and we look forward to seeing you all at the next CENT event. So thank you very much and goodbye.